I welcome you for this NPTEL lecture on earthquake resistant design of foundations. And this is the last lecture of this course. And as you are aware that we are under the 6th module of the course. This is the last module of the course, which is miscellaneous. And under this module, today we are going to talk a very important topic, that is codal provisions for earthquake resistant design of foundations. Let's say this the 6th module of this course, that is miscellaneous items, and under this miscellaneous items, these are the different sections. We have 4 chapters. So the first chapter was on raft foundation numerical examples. Then in the last 2 lectures we discussed shallow foundation on slopes, and today we are going to talk about codal provisions for ERDF foundations. So when we talk about codal provisions for earthquake resistant design of foundations, we are going to discuss 2 codes. One is Indian Institute Codes 1893, published by Bureau of Indian Standards, Part 1, published in 2016. That is the latest version of that code. And another is American Society of Civil Engineering, code number 7 with section 16. Let's discuss the first one, which is most relevant to us for earthquake resistant design. Then you know that first of all, what is given in this code related to the soils or foundations that we are going to discuss. So what I'm going to discuss is basically taken from this code only, and I'm going to explain each and every part and what is its implications. So first of all, when we talk about the design of foundations, then unfactored load shall be combined in line with other relevant Indian codes while assessing the bearing pressure in soils. So first of all, unfactored load will be. However, when earthquake forces are included, net bearing pressure in soils can be increased as per table 1, which is depending on type of foundation and type of soil. So see, here it is basically percentage increase in net bearing pressure and screen friction of soils. So this is depending on basically on type of soil only. Earlier code was on type of foundation also, but still there is some typo there, and it is only depending on type of soils only. So there are 3 types of soils mentioned in this code. One is rock or hard soil, then second is medium or stiff soils, and then type C is soft soils. These types of soils has been defined later in table 2, but before we discuss table 2, let's say for these 3 types of soil, A, which is in general rock or hard soils, you can percentage increase in allowable bearing pressure by 50%. If your foundation is passing through type B soil, then the increase when you consider earthquake load should be 25%. But if your foundation is on the soft soil, then there should be no increase in for bearing pressure irrespective of type of foundation. So first of all, this is depending on type of soil only. For determining that this is classified in 4 types as given in table 2, which we are going to discuss. In soft soil, no increase shall be applied in bearing pressure because performance cannot be restricted by increasing bearing pressure. So as we've seen here, that percentage increase in case of soft soil is 0. Now below this table in the code, there are notes which we will go very quickly. First of all, the net bearing pressure shall be determined in accordance with IS 6403 or IS 18888. So whatever the net pressure is determined, and if you are considering the earthquake load, then according to table 1, the net bearing pressure can be increased for medium and rocky sites. Then only corrected values of N shall be used when for determining N is coming later. If any increase in net bearing pressure has already been permitted for forces other than seismic forces, the increase in allowable bearing pressure when seismic forces is also shall not exceed the limits. So that means, suppose due to some other consideration, you have already increased the net bearing pressure of the soil, then total increase in any case, whether you consider this earthquake forces or not, this should not go when you consider earthquake forces, then total increase should not be above this limit, the 25 or 50. So suppose already due to some reason in the first type of soil, you have already considered 25% increase in allowable soil, then another 25 can be considered when you consider earthquake loss. Then, despite the desirable minimum corrected field values of n shall be as specified in this table. What this table says? This table is based on seismic zones. So, if your site is in seismic zone 3rd, 4, and 5, then in case of for depth below ground level, which is less than 5 meter and more than 10 meter, then n values, minimum L values should be between 15 and 25. That means if your site is lying in this 3rd, 4th, and 5th zone, up to 5 meters below ground level, minimum N value is for earthquake condition should be 15. And if you are going beyond 10 meter down, then it should be 25. These values for second seismic zone is 10 and 20. And what are the seismic zones which we are going to come later? So now the issue is here between 5 to 10 meter, the linear interpolation can be used, and below 10 meter depth, then it should be the flat value, the minimum value. So we can say that these are the minimum N values. But suppose if these N values are not available, in that case, if soils of lower N values are encountered, then those sites in these tables, then suitable ground improvement techniques shall be adopted to achieve these values. Alternatively, deep pile foundations should be used, which are anchored in strong data underlying the soil layers that will meet the above requirements. Piles should be designed for lateral loads, neglecting lateral resistance of those soil layers which are liable to. If suppose the piles are passing through the liquefiable soil layers, then determine the pile capacity, load carrying capacity of the pile. Those liquefiable layers should be neglected. Next, Indian Standard Codes IS 1498 or IS 2131 may be referred for soil location and corrected N values will be determined by applying the correction factor Cn for effective overburden pressure, sigma V naught, using relation N equal to Cn into N1, where N1 is the uncorrected SPT value and Cn is the correction to be applied for overburden pressure, which can be applied using this relation root PA divided sigma 0 effective. So, and the value of Cn, maximum value of Cn is where a cap is put, should not be more than 1.7. So, if from this formula, if you are getting the value of Cn less up to 1.7 or less, then it's fine. Otherwise, suppose if you get a higher value than 1.7, then Cn should not be taken more than 1.7. In this equation, Pa is the atmospheric pressure, and continue with that. What you have when you want to use this table, which is table under node 4, then for using this table, the value of N to be considered shall be determined as below. For isolated footing, it should be below the base of the footing. You need to find the average value of the N below, starting from the base of the footing to the up to 2 times the depth width of the footing. Then in the second case for raft foundation also it is the same. That is from starting from the base of the footing up to 2 times the width. But in case of pile foundation, then it will be below the pile tip up to the 2 times the diameter of the pile. And for good pile foundations, again bottom tip of pile group to the width of the twice the width of the pile group should be considered. For well foundation, it is similar to pile foundation. That is starting from bottom tip of well to depth of bottom tip of well plus twice the width of well, 2 times of the width of the well. So that much zone should be considered, and accordingly you can determine the value of N. Now coming to that, when we continue with this in reference to table 4, where the minimum prescribed N values are given. But suppose if you have soil deposit which consists of submerged loose sands and soils which are falling under classification as P, that is means basically poorly graded sand, with corrected extended penetration test values N, which is less than 15 in seismic zone 3rd, 4th, and 5th, and less than 10 in seismic zone 2nd. In that case, the shaking caused by earthquake ground motion may cause liquefaction or excessive total and differential settlements. And such sites should be avoided, preferably for locating new structures, and should be avoided for locating structures of important projects. So first of all, if you have some sites where N values are less, if less than let's say 15 in seismic zone 3rd, 4th, and 5, and less than 10 in seismic zone 2nd, then we should avoid those sites for construction or otherwise we need to use the ground improvement as site clear. And this is particularly applicable for new projects or for locating the structures of important projects. If that is not possible, then in that case, otherwise settlements need to be investigated and appropriate methods adopted of compaction or stabilization to achieve N values indicated in Note 4 of this document. Alternatively, deep pile foundation may be adopted and anchored at depths well below the underlying soil layers, which are likely to liquefy or undergo excessive sediments. So here, one way that we should try to avoid this. But if you can't avoid, then we need to check the settlement that they should be within the permissible limit. And if it's not, in that case, we need to stabilize the soil. So until you achieve the N values as mentioned in the table. Also for marine clay layers and other sensitive clay layers, which are known to liquefy, undergo excessive settlement or even collapse owing to low shear strength of the soil. Such soils will need special treatment according to site conditions, and that is we need to see the table 2. And another issue is simplified method is given in another app for evaluation of liquefying potential for designing before you design for foundation. So let's see what is given in table 2. Table 2 is nothing but it gives the for using table 1 you need the classification of the, and in table 2 the soils are classified under four categories, not 3 only. Type A, Type B, and Type C. Type A is rock or hard soils, Type B is medium or silty soils, and Type C is soft soils. So these 3 types A, B, C are the same as given in table 1. But one more type is D is added here. Let's talk about D first. D is for unstable, collapsible, liquefiable soil. So for type D, it requires site study and special treatment according to site condition. So special treatment will require for type D. So that will be beyond the scope of the code which has been given. But let's say for type A, type B, and type C, how they are defined first of all. Type A is well-graded gravels or well-graded sand, that is it could be GW or GSW. Both is less than 5% passing through 75 micron sieves. So it is micron, here it is not mm. And then well-graded gravel, sand mixture with or without fines. Then poorly graded sand SP or clay sand, all having N above 30. So if you have N, first of all, the value of N should be greater than 30, and type A will be normally well-graded gravels or well-graded sands, but not if you have poorly graded sand or clay sand, then one need to make sure that the value of N is above 30. Then you can consider if it is N value is above 30, then in that case we can consider this is the type B. But if N is not 30, then it goes to type B, provided the N is between 10 and 30. And this type B is applicable for poorly graded sands or poorly graded sands with gravel with little or no fines having N between 10 and 30. Then this is also applicable for clay sites for the low compressibility. Type B, for the type B you require that either it could be silt ML or it could be clay CL. But for type C is applicable for all soft soils other than SP which have N less than 10. In case of N values less than 10, and the various possible soils are silts and clay of intermediate and high compressibility. So if you have intermediate compressibility or high compressibility, it will fall under type C. It could be silt or it could be clay, so it could be MI, MS, CI, CH, or combination of those. So that will fall under type C, that is soft soil. Type D we have already discussed. So accordingly, whether your soil is falling between type A, type B, type C, then you can determine that which type need to be used in table 1. Now continue with that. One of the most important part of the this IS 1893 that it defined design acceleration spectrum for design acceleration spectrum. This gives you the design horizontal seismic coefficient AH for a structure. This what is AH? AH is nothing but design horizontal seismic coefficient, and this is simply given by Z by 2 SA by G R by R. So Z is called here zone factor. This is given in table 3. SA by G is basically your this SA by G is basically spectral acceleration, which is given in that. I is importance factor given in IS 1893 parts 1 to 5 for the corresponding structures. When not mentioned, the minimum value 5 shall be taken as here. It is not mentioned. So I importance factor should be taken 1.5 for critical and lifeline structures, 1.2 for business continuities, and 1 for the rest of the structures. So I importance factor is selected, Z zone factor is given, and before we move ahead, for designing the seismic flows, the country is classified into 4 seismic zones, which is shown in this figure. Most of you may be aware about the seismic zoning of the country. Here you have highest zone seismic zone 5, all of the northeast, Andaman Nicobar Islands, and then some part of the Bihar. That is basically North Bihar. Then parts of Uttarakhand, where Pithoragarh, Almora is there. Then part of the Himachal Pradesh, Mandi. Then part of J&K, that is capital Srinagar. And then you have in the Bhuj, Kutch also, in the Bhuj region. It is basically Kutch region of Gujarat. Here also, this is in seismic zone 5, where the earthquake of 2001 struck. So this, and then green line is here. Dark green line is saying seismic zone 4. So for example, Delhi, Dehradun, Roorkee, all are falling in seismic zone 4. Okay. So we continue with this. So according to, there are, you may be aware, there are 4 zones only: second, third, fourth, and fifth. There is no first zone. As seismic zone factor for second zone is 0.10, for third seismic zone is 0.16, fourth is 0.24, and finally highest seismic zone has a zone factor 0.36. So this was table 3. Now in this equation, A Z by 2 SA by G, so we already discussed about Z and I importance factor. What is R? R is called response reduction factor, which is given in IS 1893 parts 1 to 5 for the corresponding structures. So whichever code you require, the values are given, their response. Then SA by G in this case is called design acceleration coefficient for different soil types, normalized with P ground acceleration, corresponding to natural period T of structure. So considering the natural period T of the structure, SA by G, which is design horizontal acceleration coefficient, is determined, and this is a coefficient, and this is normalized values P ground acceleration. So that means to convert SA by G into SA, we multiply by P ground acceleration. It shall be as given in parts 1 to 5 for IS 1893 for the corresponding 5% damping given by expressions below. So this is like SA by G value can be determined from this expression, but rather than using this expression, let's come straightforward to the figures. There are 2 methods suggested by IS 1893 for response spectrum. One is called spectrum for equivalent static method, which is shown here, and another is design acceleration coefficient SA by G, which is corresponding to 5% damping. So both have the damping in the system same. Both are plotted on natural period, and both determine the value of SA by G. Now, in this case, SA by, what is the difference between these two? There are 3 curves here in this response spectrum, and these 3 curves are for different types of soils. The lowest one is for type first, that is rock or hard soil. Medium, this middle curve is for type second, that is medium soil, and the top curve is for type third, soft soil, which is that the soft soil is the concern. And you could see when you consider the soft soil, the value of SA by G is maximum here, not here. That means even after certain period, this is at the same level. So what you have here, but in this case, another figure which is for response spectrum method, you could see that this starts from value 1. All the 3 curves start from value 1, and then they become 2.5. So let's see what are the location here. So if you see the data are given here, this value from where the curves are getting reduced, it is 0.4, 0.55, and 0.67. So these are the numbers listed here. While for this case, again, this rest of the part is same. Only there is a difference between this and this is related to you have this one and then multiple. So if you see here, this is 0.1 up to 0.1 second, or irrespective of types of soil, this remains. This point belong to 0.1 second. I can pull this. This is related to. This tip is related to 0.1 second. .1 second. And this 0.1 second is the respective type of soil. In fact, up to this point, all the curves are going together. And after that, they started diverging. So these points we have already discussed that this is the 0.4, this value was 0.1, this is 0.4, this is 0.55, and 0.67. So this way, you have that this flat curves. Let me erase this one because it's causing. So what you have here is basically you have response spectrum, and one is using equivalent static method. And what is done for a given structure, we find that its natural period, and for the natural period, we find the corresponding the value of SA by Z. Okay. And this SA by Z is for 5%. So we are done with this. Now continue with that. For determining the correct spectrum to be used in the estimate of SA by Z, which is coming here. Then the type of soil in which the structure is placed shall be identified by the classification given in table 4. So in table 4, soil type first is rock or hard soil. Soil type second is rock, medium or steep soils, and soil type third is soft soils. So all soft, medium, and hard soil, all three soils have been covered. And in table 4, the value of N to be used shall be the weighted average of N soil layers from the existing ground level to 30 meters below the existing ground level. As the N values of N shall be the corrected values. So first of all, you will be using corrected values of N here. Let's discuss first for soil type. First for hard soil. So continue this. So what you have here, this table is similar to what you have in table 2. You have 3 soil type here: rock or hard soil, medium or steep soils, and soft soils. And the definition is more or less same. But you can see here, this well-graded gravels or sand, both with less than 5% passing 75 micrometers C. That means basically it is micron, and that should be corrected in the last. So, and another for the rock side, you have well-graded sand mixtures, poorly-graded sand, poorly-graded sands, or poorly-graded sands with gravels. So, if any of these things are encountered, then it can be. What I can suggest here, that if you have the value of N is above 30, then you can use rock or hard soils. But if it is between 10 and 30, then medium or steep soils should be used. Finally, for soft soil, the value of N is less than 10, and rest of the things, its applicability is for basically intermediate and high compressibility soils. So these are applicable. But if intermediate is low, then this method, soft soils, may not be applicable. So this was all about this Indian Code 1890. Now let's discuss what is the provision given by American Society of Civil Engineers, and that is part 7. Here, the foundation shall be designed to resist the forces that develop and to accommodate the moments imparted to the structure and foundation by the design ground motions. The dynamic nature of the forces, the expected ground motion, the design basis for strength and energy capacity of the structure, and the dynamic properties of the soil shall be included in the determination of the foundation design. So when you have foundation design, in that case, these all need to be included. That is the recommendation of ASC. Continue with that. They have in ASC the load deformation characteristics has been given. The linear load deformation behavior of foundation shall be represented by an equivalent linear stiffness using soil properties that are compatible with soil strength levels associated with the design application. So that means it is basically what you can say the equivalent linear model of soil, where you keep updating the shear modulus and damping ratio of the soil as the level of strength changes. But here now it is saying that this is the final because there is no change in the strength. So that we need to use the strength compatible shear modulus G and the association compatible shear velocity Vs for the equation of equivalent linear stiffness. Then a 50% increase and decrease in stiffness shall be incorporated in dynamic analysis unless smaller variation can be justified based on field measurements of dynamic or direct measurement of dynamic formation stiffness. The largest value of response shall be used in the design. So first of all, 50% increase or decrease is possible for dynamic analysis. But as said earlier also, that suppose it is done there is some increase already in in stiffness, then the total should not exceed 50% when you consider the earthquake load even for variable types. Now coming to this reduction of foundation overturning effect of the soil foundation interface are permitted to be reduced by 25% for foundation of structures that satisfy both of the following conditions. The first condition is simple. The structure should be designed in accordance with the equivalent linear force analysis. When the structure is not an inverted pendulum or cantilevered column type structure. So that means both of these aspects need to be looked after that. And otherwise, effect under soil foundation interface are permitted to be reduced by 10% for foundations of structures designed in accordance with the model analysis. So if any structure is designed according to model analysis, then we can use it. Now coming to the nominal strength suggested by the ASC, the nominal foundation geotechnical capacity QNS shall be determined using any of the following methods. What are the methods? First step is presumptive load bearing values by a registered design professional based on geotechnical site investigation that include field and laboratory testing to determine soil classification and as required active, passive, and address soil strength parameters. So this is basically kind of a that fast track. So if you have a registered design professionals based on geotechnical site investigation, in that case you can have this the determined soil classification and active passive soil strength parameters. The third is by institute testing of prototype formations. So first is presumptive, second is talking about the registered design professional, and third one is testing of prototype formations. Nominal strength values are permitted to be based on either a limitation of maximum expected foundation deformation by the nominal strength that is associated with an element. So this can be explained here. For nominal strength, soil strength parameters are for competent soils that do not undergo strength degradation under seismic loading. In that case, strength parameters for static loading conditions shall be used to compute nominal foundation geotechnical tests. And for seismic design, unless increased, seismic strength values based on site conditions are provided by a registered design professional. Continue with that. For sensitive cohesive soils or saturated cohesionless soils, the potential for earthquake-induced strength degradation shall be used. So these are the protocols, this ASC. Then further, the ASC courses, the resistance factor shall be used for vertical, lateral, and local resistance, all foundation types. Nominal foundation geotechnical capacities QNS shall be multiplied by the resistance factor phi, which is shown in the table, or alternatively, a vertical resistance factor phi equal to 0.80 is permitted to be used, and the normal strength is determined by institute testing prototype foundation. So these are the restrictions, and in this table, one is for vertical resonance, another is lateral resonance. Now, pile soil interaction should be considered, and pile moment, shears, and lateral directions used for design shall be established, considering the interaction of the shaft and soil, where the ratio of the depth of embedment of the pile to the pile diameter or width is less than or equal to 6. That means depth of embedment is less than the this ratio of less than 6 times of the ratio of length of the pile to divided by the diameter of the pile. That is L by D basically. The pile is performed to be assumed to be flexurally with respect to the soil. Then pile group effects. Pile group effects from soil on lateral nominal strength shall be included, where pile diameter center to center spacing in the direction of lateral force is less than 8 pile diameters of width. In that case, pile group effects on vertical nominal strength shall be included, where pile center to center spacing is less than 3 times pile diameter of width. Continue with this. Then there is a provision for requirements for foundation liquefiable soils. And he has been aware that soil strength is lost when it is subjected to liquefaction. In MCG, earthquake motions, structure shall be designed to accommodate the effects of liquefaction in accordance with the requirements given in the sections. Then foundation design should support gravity and design earthquake loads using the reduced soil bearing capacity, considering the effects of liquefaction caused by MCG earthquake motion. The anticipated lateral spreading different values and shall be permitted to include the mitigating effects of any plant ground movement of the site. So naturally, these are the measures required if you have the issue related to liquefaction. Continue this. These are the references which are used for this presentation. First is IS 1893 2016. That is the criteria for restoration design of structures, Part 5, published in recently 2016. Then IS 6403 1981 is also a core practice for determination of bearing capacity of shallow foundation. By this is published also by BIS. Then ASC guidelines, SCI 716. Minimum design loads and associated criteria for buildings and other structures is given in score, and this is for evidence that is civil engineers. So with this, I thank you very much for your kind attention.